Hey, it's Jim, and this is level 1 of the CFA program, the topic on quantitative methods, and the learning module on statistical measures and asset returns. This learning module can really be summarized in the following example. I'm guessing that you do the same thing that I do every morning, get up and get in your car or the bus or a train, and you expect to arrive at your destination. I drive to school every day. And I have an expectation of how long it's going to take me to get there. I'm guessing my mean time to get to school is probably 18 minutes. But sometimes there's no traffic and I can get there in 14 or 15 minutes. Sometimes there's a wreck or sometimes there's construction. That could take me 29 or 35 minutes. So this learning module really teaches us how to measure statistical measures, how to measure that expected value, and then what I call how wrong can you be around those expectations. The Institute and statisticians call that dispersion. Remember that term as we go through the slide deck here. But so you're going to have to do a lot of calculations here in this learning module. But what's even more important is that these tools that we learn inside of this learning module are going to be applied in level 2 and in level 3, so you might as well learn them now. Just 4 OLSs, but notice calculate, 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 and then interpret. So we got lots and lots of stuff to do. So we'll do central tendency, that's going to be the expected value of the mean. We'll do dispersion, that's going to be, among other things, a standard deviation. And I remember this very clearly from my stats days in graduate school. Had a professor who said, look, first moment of the distribution is the mean, second moment of the distribution is the standard deviation, third moment is skewness, fourth moment is kurtosis. So they all go together. Those first three learning outcome statements, they could be combined into just one. Now, I don't think the Institute is going to emphasize here, especially at level 1, skewness and kurtosis, but you need to know those definitions, and we have some good slides. I'll show you those here in just a minute. But as we get into level 2 and we do all sorts of advanced quantitative analysis, skewness and kurtosis are going to be way more important than they are just here in the introduction. And then we'll end with a conversation on correlation. So let's go ahead and begin with measures of central tendency. I'm guessing that you know these already, the mean, the median, and the mode. One of the things I thought was interesting in this learning module that was fairly different from stats textbooks is that the Institute doesn't seem to be too terribly interested in the population mean or the population standard deviation, which is fairly good news for you guys who are taking this level 1 exam. But as we go through this, we'll do a little bit of a differentiation between population and sample. But if you look at the questions at the end of these learning modules, they almost never say something about the population. So I don't want you to ignore it, and I want you to know the definition, but I don't think you'll have to calculate it. But you might have to interpret it. So think about the population is all of the observed values in a population. A lot of times, in fact, most times, it's almost impossible to get the entire population of observed values. So you just take a sample. Even if you have a population of, let's say 10,000 stock returns, you know how long it takes for you to go and collect all those 10,000 and put them in an Excel spreadsheet, try to figure it out. Why don't we just take a sample of maybe 100 or 200 and we don't have to worry about collection. So there's always a trade-off between the cost of collecting population data versus the efficiency of just using a sample. So look at those equations there. Uppercase N for population, lowercase n for the sample. All we're going to do, didn't we learn this in kindergarten? You just add them up and divide by n. Bobby has 8 apples, Cindy has 4 apples, Jimmy has 3 apples, Teddy has 17 apples. What's the sample mean of the apples in the kindergarten class? Now look down at the bottom arrow point here. I'm always careful about this. The Institute wants you to believe that the arithmetic mean is a really good, in fact, it uses the word excellent measure of performance, but I kind of changed that there. I mean, it's a first measure of performance, right? Just because something has happened in the past doesn't mean it's going to repeat itself in the future, especially the near future. So notice what we put on the slide deck. It's a first measure of a forward-looking performance. The median, this of course is just the value that occurs right in the center of the data. The mode is the one that's most frequently observed. So if there's just one mode, that's called a uni. And if there are multiple modes, that's called a bi. Yeah, look at the bottom arrow point there. This is probably a really good exam question. We're always going to have, let me go back here. We're always going to have a mean. We're always going to have a median, but we might not have a mode. So think about collecting data on stock returns or bond returns or collateralized mortgage obligation returns. And suppose you collect, 100 or 200 or 500 days worth of daily data, and you throw it into an Excel spreadsheet. What you're tempted to do is go ahead and sort that column and take a look at the outliers. So the question then becomes, what do you do with outliers? Suppose that you have, let's just do 100. Suppose you have 100 of them and 97 of them are coagulated within some reasonable range. But then you have 2 outliers up here, 2 outliers down at the, 2 up here and 1 down at the bottom. What do you do with those outliers? Well, I'm going to go ahead and say, let's do option 1. Let's do this all the time because this is what my professors, when I was writing my dissertation, taking all my classes, they said, don't. You're going to be tempted to sort your data, but just don't do it because if you know your observations are accurate, and we had access to data of daily stock returns that, we just assumed coming out of the University of Chicago that they were accurate. So, we didn't want to do anything with the outliers. So option 1, the best option is if you know that these observations are accurate, then you're not going to do anything with the outliers. But then sometimes you have estimates. I mean, let's just take a simple example. Suppose instead of collecting days worth of stock returns, you're trying to estimate the returns on, some ancient Roman coin. Well, you're not going to have daily data. You're not going to have weekly data. Maybe you'll have quarterly data. Maybe some of these coins change hands. You could probably get quarterly data. But if you wanted to go ahead and try to estimate with an appraisal, we'll learn all about this when we do some other quantitative method stuff in level 2. So you have some appraisal values in there. Well, suppose you get some guy who appraises this coin and says, oh, this coin is worth $10 million. And you have all these other coins and they're only worth 500,000 and 700,000. What do you do? What do you do with that? Well, one of the things you can do is just ignore it. You can just eliminate all of them. But you can do it a couple of ways. You can do a trimmed mean. So you can just say, you know what, we're not going to eliminate just that $10 million appraisal estimate, but we're going to eliminate the top 2% and the bottom 2%. So that would be a 4% trimmed mean. Or what you can do is substitute values in for those outliers. This is called a Winsorized mean. And so what you do is you just take a look at that, the 2% and the 2% at the top, 2% at the bottom, and you go ahead and you just assign some values in there. Maybe you take the mean, maybe you do a probability distribution. I mean, there are a bunch of different ways that you can do this, but just remember the trimmed mean. What you're doing is you're throwing out the tails. At the Winsorized mean, you're not throwing out the tails, but you're kind of substituting some values in there that you think are reasonable. Who knows what you think are reasonable could be. But make sure when you're answering this question on the exam that you don't do something crazy like, oh yeah, let's just do this or this or this. That doesn't sound reasonable. Now this is a big LOS from my interpretation. I try to tell you guys that every LOS is a potential exam question, but this one here, there's a big problem inside of the learning module, and then there's an equally big problem at the end of this learning module. So it's important for you guys, at least I think it's important. This is a signal that the Institute thinks this is important. So I think we should go through one of these examples of locations. So we can have this data set. So think about it in an Excel spreadsheet. So we can chop it into lots of parts. We can chop it into 4 parts. We can chop it into 5. We can chop it into 10. We can chop it into percentiles, which are equal parts out of 100. We could chop it into eighths or 14ths or 22nds. You remember that old great Steve Martin line where he goes, okay, half the audience do this, half of the audience do that. And then he goes, and 2/7 and 5/7. That's super silly stuff. But of course, you're not going to do 2/7 and 5/7 on the exam, but you'll do probably 4 parts or 5 parts. So make sure you know these definitions. Look down at the bottom. If we're doing percentiles, there's an equation down there to get that percentile. We'll do an example here. So you ready for this? We got daily returns on a global fixed income index over the past 5 years. Now, in the learning module, there's another column out there for number of observations. I think it's in the 60s for each one of these bins. We didn't duplicate that here because that's not too terribly important of a column. So, you've got 5 years, and we're going to rank them from 5% to 5% to 5%. So we have 20 bins or 20 buckets going down the left-hand column, and then we just aggregate them, 5 and 10 and 15. So that's the next column. And then we have lower and upper bounds. So just think of those as ranges inside of each of these bins. Now, a couple of things to note here is that the Institute emphasizes that these returns are continuous in nature. And so a return that falls in the range of a minimum, it's going to be in the 1, and the maximum, it's going to be in the 20. So we just arrange it so that you can throw those all into to each one of those bins. All right, so let's take this data and let's do 5 questions. So here are really, really good 5 questions for the exam. Can't imagine that you would get all 5 of these, but you know what? If you know all 5, then you can do 2 of them. All right, so let's do the 10th and the 90th percentile. So all we're going to do, we've got 20, right? So that's 10 percentile. And so all we're going to do is take the upper bound, what is that, a minus 2.1%, and lower, that would be in the 10th percentile. So when I hit the down arrow here on my keyboard to get the 90th percentile, what you're going to see is the green coloring goes all the way down to the 18th bin. So remember, when you say 10th percentile, we're going up to the 10th percentile. And then the 90th percentile, we're going up to the 90th percentile. So there we go. And we changed colors from green to light red. So there you go, 2.7, which is the lower bound. So make sure that you do that. Go to the green when you're going to there, and then you go to the 2.7%. So 90% of them are 2.7% and lower. How about the first, second, and third quintiles? So there's 20, so that's 20 divided by 5 is 4. So there you go. You got the minus 1.5, then you got the between the 1.5 and the 0.3, and then between the minus 3, which is the last one here, right? So that should make sense. And then the 0.9. So there's the first, second, and third quintiles. There's the median. This means that this falls exactly in the middle. You got 50% on the left side, actually 50% on the up top side, and 50% on the below side. And then the first and third quartiles, well, we'll just do the same thing here. So we'll go down to the 120, then we'll go down to the 180, and then we can take the difference between the two. The minus 180, a minus. Don't forget to do the double minus there. So there you go. You have 3%. So that takes us through all of those quick examples. I did them quickly, but this is what I want you to do. Go to the learning module, look at that example inside of it, then go to the end of the learning module and work through that problem. You should be fine. All right, how about if we have a table with annual performance of an investment fund? So there we've got 10 years. Let's do this third quintile. So we're going to just do the same thing. So look in that, what is that, third box? What are we doing? We're just ranking them. So imagine that you're taking this test in an Excel spreadsheet. So what you would do is highlight that second column and then just do a sort function from low to high. And you would get in that third box, you'd get in parentheses from the -10 all the way up to the 20.8. So what we need to do is figure out what is that third quintile. That's 60%. So we're going to do n plus 1. Let's go back up to the second box. We're going to do, and this is that equation I was telling you about just a few slides ago. So n plus 1, we have 10 observations down the left-hand side. That's 10 years plus 1 times 60 over 100. So that gets us 6.6. So then we're going to use this linear interpolation down at the bottom. So it's another formula for you to memorize. So all we're going to do is take the sixth one, which is the 7.25, and we're going to add something to it. So you have the X observation at the 6th year, which is 7.25, or the 6th in order, right? The year in order. And then we're just going to adjust it. We're going to just add some adjusting factor. And that factor is really just kind of a weighted average of two things. We're going to take the difference between the 6.6, which we got from above, and the 60th percentile, and then the difference between those 6th and 7th entries. So we're really, can I just say this? Don't tell the Institute that I told you to do this. Just take an average of those next two numbers. You probably get close to it, although the Institute might give you the average, the exact average, as one of the answers. So at least if you take the average, you're going to get somewhere around 6.6. All right, here's a picture of the interquartile range, which we did a few slides ago. This is called a Box-and-Whisker plot. So you have the range, so you got the top and the bottom, the top and the bottom, the min and the max. And then you can look at the mean and the median, and so there's the third quartile and the first quartile. So that's a good picture there. It'd be cool if the Institute gave you this picture in addition to giving you the data points. Then it'd make it a little bit easier for you. All right, so what did we do in that first LOS? We did like the expected value. This is the, 17 or 18 minutes of how long it takes me to drive to school every day. And notice that we had several different kinds of measures. We had the mean, or the expected value, which was my 17 or 18. But then, I don't ever collect this data, but I guess over the next 30 days, I could write down what time I left, what time I got to school. So I could do, with that data, I could compute all of those measures of central tendency that we did on those last handful of slides. I could do the first quartile and the 12th quartile and the 400th and, whatever that is. So what does that summarize? That summarizes points of central tendency, right? What do we expect to get out of riding to school every day? What do we expect to get out of a global investment fund? What do we expect to get out of a portfolio of C-rated fixed income securities, right? Point of central tendency. But then we have to ask ourselves the question, and I said this in the introduction, we have to ask ourselves the question, how wrong can we be? What's the maximum wrongness? That's not a word, but I think you know exactly what I'm suggesting. I could get, when I go to school, I get on an interstate, and if there are no cars on the interstate, I could do 100 miles an hour to get down there. It's probably, I don't know how long I'm on there, maybe 8 miles. I could do that in 2 minutes, right? I probably wouldn't do that because my car wouldn't go 100 miles an hour, and it would be violation of the laws of my state. But suppose there's a wreck and I'm sitting in traffic for 30 minutes or 60 minutes or 5 days, whatever that is. So what we need a measure of how wrong that point of central tendency estimate is going to be. Like if I get in my car tomorrow and I drive to school, and it takes me 18 minutes and I expected to get there in 18 minutes, well, I was exactly right. But I'm not going to be exactly right every day. So we need these measures of dispersion. Notice on the far right up at the top, variability around that point of central tendency. So there's a range. We did the range right back here, right? There was a maximum and a minimum. So we kind of introduced this concept of variability. But the range, that gives you some idea, right? I could say to myself, you know what? The most time that it's ever going to take me to get to school is 40 minutes. Therefore, I could leave my house at 7:20 and be guaranteed, well, I don't want to say that, be guaranteed to get at school at 8 o'clock so I could teach my 8 o'clock class. But then what happens if I, like have a heart attack or something? That 40 minutes is going to be longer than 40 minutes. Maybe that's the rest of my life. I never get back to school. So what we need to do is we need to take that range, the minimum, the max, and we need to say something like, all right, let's chop this into pieces. And that's what this mean absolute deviation does. So all we're going to do is take, each observation minus the mean observation. So it takes me 18 minutes to get to work on average, right? So one day is 27, one day is 14, one day is 22, one day is 18, one day is 40, right? So all I'm going to do is sum those and divide by the number of observations. Now, if the Institute gives you one question on range and mean absolute deviation, you're going to high five yourself, because these, you'll see this in an example. These are super easy. What's a little bit challenging here is to go ahead and compute the population variance and the sample variance. And then when you take the square root of each of those, then you get the population standard, the population variance, the sample standard deviation and the population standard deviation. And so look at those equations. What you're doing is you're summing a squared term. So this gives you, back here, we're just summing a difference. But now we're summing a difference and then we're squaring it. So there are lots more chances on the exam for you to make a mistake. But I'm going to eliminate all that confusion here in just a second. So the big difference, and remember what I said earlier, population, you always divide by n. Sample variance here, we're going to divide by degrees of freedom, which is n minus 1. So I think the exam question is probably not going to be compute population variance, but compute sample variance. So if they say something about population, always remember divide by uppercase N. All right, let's take a look at an example here. Let's do a sample of 6 financial analysts. So there we go. Large cap stocks, 2021, 6%. 7, 12, 2, 3, and 11%. Let's go ahead and do all these things that we just talked about. You ready? Now, what did I say just a few moments ago? We learned how to compute the mean in kindergarten. So you're tempted to go ahead and do this, to add those numbers and divide by 6. You're tempted to do it, and by all means, go ahead and do it. However, when you want to calculate the standard deviation, it's going to become a little bit more complex. But before we do that, let's go ahead and compute the mean absolute deviation. And I wish I could give you a shortcut, but I can't. So look at that equation there. You're going to have to take the difference between each one, 6% and the mean, 683, 7% and 683, right? And sum those and divide by 6. If you do all that, you get 3.17%. I wish there was a shortcut, but there is not. To compute the variance, now look at this equation. Now we're going to do the same thing. We're going to take the 6% minus the 683, and we're going to square it. We're going to take the 7% minus the 683, and we're going to square it. But since we were told a sample of 6 financial analysts, we're going to go ahead and divide by n minus 1. We're going to go ahead and divide by 5. And there's the answer, 1657. And then on this next slide, if we go ahead and take the square root, 0407. And so this is what you ought to be thinking. You ought to be thinking, boy, I sure hope the Institute doesn't give me any more than 5 or 6 inside of the sample, because, you're trying to figure this out and you're writing. Did I square that one? Did I not square that? Did I add it? So let me go ahead and show you how to do this on a calculator. All right, I've got out my trusty 12C. I'm hoping that most of you have the 12C. Those of you who have the Texas Instruments, you can do this same thing. I'm sure you can find it somewhere out there. You're going to use your stat function and your data function. So look under the 7 and the 8. You're just going to enter the data, and you're going to then hit your stat function, and it'll give you all that stuff. But I'm hoping that most of you use this calculator here. So all we're going to do is see this sigma plus button down here. We're going to go ahead and hit our sigma plus button. We're going to enter the 6 sample data points. And by the way, do you guys know how to do decimals? Here, hit your gold 7. Do you want 7? I don't want 7. Hit your gold 3. I like 3. So you can always do gold and however many decimals that you want. I've always found 3 is sufficient. All right, so watch this. We're going to do 6 and hit our sigma plus. Notice it pops up a 1. That tells us that that's our first data point. Then we'll do 7. And there's our second data point. Then we'll do 12. There's our third data point. 2, sigma plus, 3, sigma plus, and then 11, sigma plus. So you see how it flashes a 6, 1, 2, 3, 4, 5. So if the Institute gives you 627 of these, you'll have to hit it 627 times. If the Institute gives you 627, you need to stand up and say, I'm protesting this exam. Of course, they're not gonna do that. All right, so look down here. Do you see under the 0 button, there's an X bar, and under the decimal button, there's an S. So we're just going to hit the blue X bar. So there we go, 683. We're going to hit the blue S. There we go, 4.07. How much easier is that than doing all of the stuff on this slide deck. So just a quick review. If you get the MAD, you have to do it the long way. If you get the sample standard deviation, you can do it like I just showed you in a calculator. For those of you who have the Texas Instruments, we thought it'd be a good idea to put the keystrokes on a slide for you. So notice those first 2 there. I don't really ever worry about those. I'm not quite sure that you need to. You can hit the second and the stat button, and it should come up LIN, which stands for linear relationship, and then the enter, and then the second and the enter. What you could do, if you want to fool around with it, you see it goes through, it toggles through a whole bunch of different choices in there. Quite honestly, I'm not sure what all those things do, but I think if you just leave it like LIN, I've never had any problems with my BA2 calculator. All right, so you ready for this? So let's go back to the data set. We've got 6, 7, 12, 2, 3, and 11. So what we're going to do is we're going to enter those into the financial calculator. The way we do this is we're going to hit the data key. So hit your second key and then go hit the 7. You see the word data is underneath your 7. And so what will happen is that you will have over on the register, look over in the far right column, you'll have x01 is equal to 0. So your x variable, let me just go back here, 6 is going to be x1, 7 is going to be x2, and 12 and so on is going to be all the way up to x06. So you need to make sure that you enter these correctly. So let's go ahead. What do you have in your register right now? You have x01 equals 0. So hit 6. And then go up to the top and hit enter. Not the equal sign, not any other button that you have on your calculator. You have to hit the enter button up on the top. And then you're going to hit the down button. What happens then is that the calculator is going to say, all right, what about a corresponding y value? And notice that the default is 1. So just leave it like that. We're just dealing with one data set, and we don't want to enter a y data set. So the default is 1, so you don't have to hit 1, enter, just hit the down button again. And you'll have x02, right? So just do 7, and then down, down, and then 12, enter, down, down, and do all that until you get to all of them. And then you'll have entered all of these data points, right, that are in the brackets up at the top. So that was inside of the data function. Now, in order to solve, now remember the LOS calculate measures of dispersion. So in order for us to get to standard deviation, we need to move over to another function. So look under your 8, there's the stat. That stands for statistics, of course. So hit your second stat button, and you should see LIN, and then just hit your down button, and it should say n equals 6, because we entered 6, right? There are 6 of those guys, right? 6 of those. And then hit your down button, and you get the mean. There's our 683. That's from the previous slide there, right? And then there's the sample standard deviation, the 4.07. And then if you want to go down again, you could get the population standard deviation. But recall my conversations about samples and populations. So either one of these calculators will get you the correct answer. I, of course, have my preference. I get nothing. I'm not going to say anything bad about the Texas Instruments, but I've had the 12C for 1,000 years, and it has never let me down. Here's this thing of beauty right here. I took this to the exam, and back when I took the exam, I used to put little stickers on it to show that it was approved. So I took that sticker off. But the 12C doesn't ever fail you. But if you have the BA 2+, that's perfectly fine. If you haven't bought one yet, well, then maybe you could take some of my advice. All right, so what we did in that example was to take a look at the entire distribution, right? We said something like, here was our mean. What was my mean? 18 minutes to get to school. And we wanted to consider the total variability on the left-hand side and then on the right-hand side of that distribution. But there are other ways to measure dispersion. What you can do is say, you know what? I only want to worry about if it takes me too long to get to school. I don't really care if I get there early. What does this mean for stock returns and portfolios? Well, I'm worrying less about if stock returns are positive, but I want to know what happens when stock returns are less than 0, when they're negative, or when they're less than some kind of a target return. So we have the semivariance and the semi-deviation. And we have the target semivariance and the target semi-deviation. So what we can do is we just compute the semi-deviation with the mean of the distribution like we just did before. If we're doing the target semi-deviation, we could just throw some number in there. We could say, you know what, I want to worry about when my portfolio value falls less than 10% or 12% or 100% or whatever that number is. So let's do a quick example here. So we have an equity mutual fund. There we go. 10 years during the decade of the 2010s. We have a target downside deviation if the target return is 20%. So here in this case, we're saying, you know what? We want 20% out of this portfolio, but we know that over the last 10 years that only a handful of those returns exceeded 20%. So what is that target downside deviation? In other words, how wrong can we be less than 20%? Well, we need to put together a table for this. So there's the column for the years, there's the column for the returns, and then we have a deviation from the 20% target. So just do in that first row, 36 minus 20 is 16, right? 29 minus 20 is 9. And so you do that all the way down for the third column. And then over in the fourth column, you just replicate those that show up below that, below the target. And then you square them over in the final column, and then divide by degrees of freedom. Remember, this is sample, n minus 1. So there you go. The target semi-deviation is 17.21%. Now we can continue this discussion if we want to take ratios. So look at this thing called a coefficient of variation. Notice on the right-hand side we have the population again. So we have the lowercase Greek letter for sigma, and then divided by the lowercase Greek letter for mu. Those are population parameters, but here over on the left hand we have the sample coefficient of variation, where we're just taking the sample standard deviation, throw that in the numerator, and the sample mean, throw that in the denominator. And so think of what we're doing here. Coefficient of variation. We have standard deviation in the numerator, which is, and this is going to be emphasized throughout levels 1, 2, and 3, standard deviation is a measure of risk. So you have a measure of risk in the numerator and a measure of return or compensation in the denominator. So just think of that ratio, coefficient of variation. Well, let's just read the definition up there, right? Describes the amount of variability relative to its mean. How wrong can you be in the numerator versus what you expect it to be in the denominator? So let's just do a quick one. There's five observations. You should be able to get that standard deviation out with your calculator just like I did. So there's the mean of 4. Standard deviation is, mean of 40, not 4. Mean of 40. Standard deviation is about 5.5. So you do that, you get 0.138. What did I say in that introduction? Skewness and kurtosis are the third and fourth moments of the distribution. So it makes perfect sense to say something like, all right, we've been assuming a normal distribution for lots and lots of our stuff inside of level 1. We'll do this in level 2 and level 3. So there's the normal distribution in the middle. This is characterized by the mean and the median and the mode being the same number. But sometimes we can tilt to the left, sometimes we can tilt to the right. I have to be careful, I don't want to give myself vertigo. So what's that positive skewness? Well, what positive skewness means is that the expected value, right, the mean is over to the right. For a negative skewness, the mean is over to the left. So that's probably a good way to memorize this. Although, you look at the top up there. Mean is greater than the mode. This is positive skewness. Mean is less than the mode. This is negative skewness. There's an equation. Now notice the LOS doesn't say calculate skewness. We may have to do that in level 2. But for now, I don't think that you'll have to calculate it. But if you think about the 4 moments of the distribution, what did we do when we calculated the variance? We took each x, subtracted the mean, and squared it. Well, if it's the third moment of the distribution, why don't we just go ahead and take that difference and cube it, right? See the numerator there. X sub I minus x bar raised to the third power. And instead of dividing by, what did we do back in the sample standard deviation? We divided by n minus 1. We're going to divide by the sample standard deviation cubed. Yeah, so, these are lots and lots of calculations. You can do these so easily in Excel. But look at the bottom. This is probably the exam. Interpret and evaluate measure of skewness. So if it is positive, then the distribution is positively skewed. So there we have the left graph. If it is negative, then you have negative skewness. There we have the right graph over there. I think that's a great summary of potential exam questions. We'll do the same thing with kurtosis. So with skewness, we're leaning to the left and we're leaning to the right. With skewness, we're either going up or we're going down, right? You ever sing that song to your children? The wheels on the bus go round and round, so up or down. So that's really all we're doing. So we're taking a normal distribution, which is green right there, and if we stretch it up, that's a leptokurtic distribution, right? Where the peak is higher, but if we flatten out, if we have fatter tails, that's mesokurtotic. So look at those definitions there. We've got leptokurtic, we got platykurtic, and we have mesokurtic. And so all you need to do is know those definitions. What are we going to do with the formula? Well, we're going to do the same thing. We're going to take x of I, subtract out x bar, and raise it to the fourth power. So once again, look down at the bottom. We're worried about these 3 types of kurtosis. So look at that first arrow point. If kurtosis is, if you take out 3 and it's greater than 0, it's leptokurtic. If it's less than 0, it's platykurtic. And if it equals 0, it's mesokurtic, also known as the normal distribution. Now, what the Institute doesn't do here is that the emphasis is on lepto, and platy, but this is going forward, so you don't need to worry about this right now. But there's also a measure of kurtosis about how much degree is in the tails, right? In the normal distribution, the tail goes all the way out. But what if the normal distribution of the tail never hits the horizontal axis? So we have to worry about that kind of kurtosis. That's a conversation for a different day. All right, so let's finish up here with covariance. So we have two variables, and we know that these two variables, they can operate independently. So think about one variable, X variable, being monthly stock returns, and think about the Y variable being monthly fixed income returns. And so what we might want to know is, how do those returns move together? If stock returns go up, what happens to fixed income returns? Do they go up? That would be positive relationship. Do they go down? That would be a negative relationship. Or do they do something else? Sometimes they go up and sometimes they go down. That would be an independent relationship. So the covariance is a statistical measure of how two variables are related. There's an equation for the sample covariance. Notice, interpret correlation coefficient and by implication covariance term, not calculate. But we're doing the same thing that we just did before. Now, this is important. I want to go back here. What did we do for... Let me keep going. What did we do for... Let me keep going. Oh boy, I'm going way far back. What did we do for sample variance? We took xi minus x bar and we squared it, right? Well, instead of taking x bar, xi minus x bar, which can also be written as times xi minus x bar, instead of squaring it, which means we're multiplying it by itself, how about if we consider what happens with the other variable? So we have xi minus x bar times yi minus y bar. We divide by degrees of freedom as well. So that's the sample covariance. So the sample covariance is a measure of the strength and the direction of a relationship. Now, the problem with the covariance, and I tell my students this all the time, is that you could compute a covariance and it might turn out to be a minus 427. It might turn out to be plus 0.0000657. Or it might turn out to be a plus 4,855,000, right? So what do you do with these numbers that have such a vast difficulty in interpretation? Well, what you do is what all statisticians have done for hundreds of years. You standardize it. All right, so that's what a correlation coefficient is. It's nothing more than a standardized covariance term. When you standardize something, you always divide it by the standard deviation. Now, since we have two variables, look at the bottom gray box. We're going to take that covariance and we're going to divide it by the product of the two standard deviations. So, you ready for this? Instead of having a range of between, what did I say, minus 685 and plus 4 million something, you put it in a vise, you standardize it, you squeeze it, you squeeze it, you squeeze it, so you force the covariance to fall within a range of a -1 to a +1. That's always the case because of standardization and by definition. So what did I tell you about the covariance? It's a measure of strength and direction. Same thing with correlation coefficient. It's a measure of the strength and the direction of a relationship. But now we have this narrow band under which we can evaluate the relationship between those two variables. So if the correlation coefficient and the covariance turned out to be 0 between stock returns and fixed income returns, what can we say? We can say that when stock returns go up or down, the fixed income security has a mind of its own. It could go up or it could go down. If the correlation coefficient is +1, which it will never be between equity and fixed income securities, over any extended time period, how about if I qualify it with that? If correlation coefficient of 1, that means that if stock returns go up by 10%, then the fixed income returns go up by exactly 10%. Now, does that mean on a daily basis, 1-to-1? And the answer to that is no. What it means is that if on average the stock returns go up by 10% over the next 7 days, then on average the fixed income returns would go up by what did I say? 10% on average over the next 7 days. So it's not a daily one-to-one. It doesn't mean that if one thing happens, then the exact thing happens with the other variable. And the same is true for a negative one correlation. It means that if stock returns go up by 10% and the correlation coefficient is a -1, that means that on average, the fixed income returns are going to go down by 10%. So let's do a different one there. Suppose that correlation, what do you think the correlation between equity and fixed income might be? Maybe it's 0.25, right? So when the stock returns go up by 10%, that means on average, the fixed income returns are going to go up by 2.5%. That's what that means. So you get a sense of covariance correlation measures strength and direction of a relationship. If you can remember that little discussion, you'll be able to answer any of those things. So here's a summary of what I was just describing. No linear relationship with a correlation of 0, but there is a linear relationship when it's positive, linear relationship when it's negative. Just think upward sloping and downward sloping lines. Here we go. Boy, we've got a couple of graphs over there on the right. What are these things? Strong positive correlation. Look at that first one. What are all those things right there? Boy, they're right on top of the line. How about strong negative correlation? Boy, they're right on top of the line. But then look at the two in the middle. Weak positive correlation, weak negative correlation, moderate. And then look at the bottom right there. There's no correlation there. So there's no linear relationship. Now, this correlation coefficient concept and the covariance concept, this is going to be super important when we hit simple linear regression in level 1, and then in level 2 we're going to do multiple linear regression, and we're going to do time series. So all this stuff is super important. Now here's a great exam question. Every finance professor asks this in every college class throughout the world. The Institute is highly likely to do this as well. Does that mean if stock returns go up by 10%, that they cause the fixed income returns to go up by 10% or 2.5%, whatever those numbers were? And the answer is negative. Negative. So look at the third one there. Correlation does not imply causation. This is super important, great exam question. All we know is about how they move together, but we don't have any idea about how they relate to each other in terms of, does the chicken or the egg come first? Which one causes the other? Well, that's why we're going to spend tons of time in level 2 performing all sorts of advanced quantitative analysis to try to find causes and relationships there. What are some other things we don't like? Outliers, they can really throw things away, make the relationship seem much stronger or weaker than it really is. Some can have a very strong nonlinear relationship. So remember from your kindergarten days, y equals a plus bx. Well, that's not the only function of y. Y could be equal to a plus bx squared plus c cubed, right? So we have strong nonlinear relationships that don't show up in our simple correlation analysis. That takes us through our learning outcome statements. So what I want you to do, and this is really the easiest thing for you to do right now, is get out a piece of paper and write down at the top of the piece of paper, stock returns, and write down 10 stock returns over the last 10 years. Just do -14%, -8%, 27%, just do 10 of those things, right? And then get out your calculator and go back and compute every single thing that we just did inside of these learning outcome statements. Then what I want you to do is I want you to go look at the big old problem in the beginning of the learning module, and then work through that one. The answer is right there, and then practice one in the questions at the end of the learning module. And there are a handful of them back there as well. So, hey, thanks for watching. This was fun for me. Have a great day, and good luck studying.